Okay, so in this video we're going to look at some examples with quantifiers. And so, depending on your textbook, what textbook you're looking at, and what instructor you have, things might be written a little bit differently, and symbolism can always be a little bit different, but we've got a propositional function, Q, and we're given a domain for that function. So it might be called, it can be called the domain or domain of discourse. Ultimately what that means is that the values of x must be integers. So for instance, we couldn't plug 0.4 in for x because that's not an integer. So we might be asked, is Q of 0 true or false? And of course what that means is to put 0 in for x, and that would leave us with 1 greater than 0, so we can see that that's true. Easy enough there. Now the main point here is to start talking about quantifiers. There's two types of quantifiers. We've got the universal quantifier and we've got the existential quantifier. So we might take a look at the existentially quantified statement. There exists x, q of x. So we might be asked, is that true or false? And I think that when we looked at q of 0, we verified that that statement is true. There does exist an integer that makes the statement true. All we have to do is find one. So if we pick x equals 0, then, and there's any number of other x values that are integers that you could choose that would also make the statement true. But if we use 0 in particular, we do come up with a true statement. We could also pick out the x value. Let's see what's another one that works. I think x equals -1. That is an integer. And if we plug -1 in for x on this side, we get 0. And we plug -1 in for x on this side, we get -2. So we can see, and we wouldn't have to pick more than one x value. The existential quantifier, this symbol, only requires that you find one that works. The question is, does there exist an integer that makes the statement true? Okay, so then what about the universally quantified statement? Right, so again, we're looking at the same propositional function q, and the question is now, is that true for all integers x? Sometimes this can be a harder question to answer because it's hard to think about the statement that you've got combined with every single possible integer. There's an infinite number of integers. So one thing you might do when you get a universally quantified statement, first thing you might ask is, well, I know that statement is going to be false if I can show that there is just one integer that makes the statement false, right? Because then it's clearly not true for every integer. So we might tinker around with some things. Actually, we could probably play around with what we know about algebra. If you were just given this inequality in an algebra setting, you probably would be asked to solve that for x. So if we subtracted x from both sides, we can see that the solution to this solution to this is all x values. This would be the same as saying all x values less than 1. Right, so when we solve that in algebra, we say, well, only x values less than 1 are going to make that true. And I was just making sure that that was right. If we look back at the existential quantifier, that worked. Value less than 1, value less than 1 made that true. So what that tells us is that if we were to choose some x value greater than 1, that probably wouldn't work. So let's see. Let's say we're going to pick x equal to, I don't know, choose your favorite integer greater than 1. And if we put that into our statement, does that work? That's 6 greater than 10. No, that does not work. So we have found just one integer that makes the statement false, which means that the universally quantified statement must be false. Okay, so how would we go about verifying if we had a universally quantified statement that was true? How would we go about verifying that? Well, that might not always be easy. We could certainly look at an example. Let's say we have this universally quantified statement. And in this problem, let's say that our domain is the real numbers. I'm just going to use that double bar capital R for real numbers. It means x could be any real number, right? So this can be difficult because it's kind of hard to grasp being able to imagine every single possible real number going in for x. Right, so of course we can't get into any statements that are too difficult. Anything that's too difficult is beyond the scope of this class. That doesn't mean that there aren't some problems that'll make you think a little bit, but so let's see, is this true? I mean, the first thing you might do is, like in the last one, is there a value of x that would make this false? No matter what value for x you pick, maybe you try -2, and you try plugging that into x. Well, that's going to work because that's 4 plus 2 greater than or equal to 1. I don't know, you try some other value, 0. What happens if you plug 0 in? 0 squared plus 2. Okay, well that works. Right, and if you try this enough times, you start noticing, well, it doesn't matter what value for x I plug in here, because when I square it, that's going to be positive. Right, that's going to be positive. And if I take a positive number and I add 2, well, that's always going to be greater than or equal to 1. Right, so one way you might verify this is to just kind of write out your reasoning. Just write out your reasoning. This expression on the left-hand side is x squared plus 2 is always greater than or equal to 2, right? Because x squared is some positive number. If I take a positive number and I add 2, then I'm always going to get a number that's greater than or equal to 2. And so because of that, the statement is true. If you wanted to get into a more formal proof, what you might do is say something like this. You might just say, well, let's let's start with something that we know is true. Let's start with something that we know is true. 2 is greater than or equal to 1. That is true. And then we're going to let x be any real number right, and that takes care of that our domain has to be all real numbers. Say let x be any real number, and then we know that if we take a real number and we add that on the left side, well, the left side of the inequality must be something that's greater than or equal to 1. If we know already that 2 is greater than or equal to 1, and we add something on the left side, that doesn't change the inequality. All we did was we made the left side bigger because we added a positive number. Right, and so something along those lines might be a more formal way of verifying that your statement is true for all real numbers, but we're not going to worry about that too much in this class. If we're able to explain our reasoning as to why a statement is true, that's probably enough. And so those can definitely be difficult and might take some thought. Let's take one last existentially quantified statement. There exists x so that x squared is equal to minus 1. And again, our domain is all reals. Right, and so all we have to do here, if this is true, is find an x value so that when we square it is equal to minus 1. So you can, of course, start just trying different x values. Of course, if you plug 0 in for x, that doesn't work. If I plug 2 in for x, that doesn't work. No, 2 squared is not equal to minus 1. Of course, just randomly picking x values isn't a great strategy because there's a ton of different x values you can try. So maybe thinking about the statement that you're given is a little bit better strategy. Again, if we just had this statement, in algebra and we're asked to solve for x, we might take the square root of both sides. And if we apply the square root of both sides, we might remember that the square root of a negative is a complex number or imaginary number. And that kind of answers our question, I think, because if we know that we're looking for a real number, then that's not going to be possible, because using our knowledge from algebra, we know that the solutions to this equation are only complex. Right? So again, if we just kind of explain our reasoning, we might say something like this: the statement is false. X squared equal to 1 has only complex solutions. Has only complex solutions. Or maybe using the same reasoning as in the last example, you might say something like the value x squared is always greater than or equal to 0, right? When you square a number, it's got to be positive. Unless the number is 0, then it would be 0. So if x squared is always greater than or equal to 0, there's no way that it's going to be equivalent to minus 1. Right, so some way of explaining how we know that there does not exist a real number so that when we square it, we get minus 1.